If you want to go really high, you can do this with 3 balls. So you may have seen physics girl do this outdoors with a basketball and a volleyball and a tennis ball, I'm not sure. Here we're indoors, so I'm just going to use a soccer ball, tennis ball, ping pong ball, and we'll see how high the ping pong ball goes here. Not bad, not bad. So the question is, how can we maximize that height? Because you'll notice soccer ball pretty much stayed down, but the tennis ball bounced pretty high in the air. So what ratio of masses can we use to really maximize the effect here? So let's see, let's draw it real quick. We have a ground, and we start now with 3 masses, M1, M2, and M3, and they're all falling together, so when they strike the ground, they're all at VI. So again, we start with all the same initial velocities, but then they bounce at various velocities. So M1 goes up at, we'll say, V1 final, M2 goes up at, we'll say, V2 final, and M3 goes up at V3 final. Right? So we want to solve this and get the most V3 we can get. Our unknowns are what? Well, they're the final velocities, right? So V1 final, V2 final, and V3 final. We have known initial velocities, we have known masses, we have unknown final velocities, and we have 3 of them. And how many equations do we have? Only 2, right? We have conservation of momentum and conservation of energy. So we have to figure out what to do. Well, the solution is to not treat it as one collision. We don't have enough equations and unknowns to treat this really as one 3-mass collision. The easier way to do this is to treat it as 2 sequential collisions. So just imagine that as they fell, they separated just a little bit, kind of like we did with 2. And the first thing that happens is mass 1 hits the ground, has an elastic collision, so it reverses and goes at V1 up, or V initial up, and hits M2. That's the first collision. And then V2, or M2, moves up and hits M3. So that's a second collision. So we're going to treat this as 2 sequential collisions. So break into, this is the strategy, 2 collisions, 3, what is this? 1 to 2, 1 hitting 2, and 2 hitting 3. That's how we're going to do it. Okay, let's see what we get. So first we'll say when 1 hits 2. Well, we kind of already did that. That was the previous video on the bouncy balls. You get the max height if what? If V1F equals 0. Okay, we solve this by saying, make this one just sit, which occurs if, what was it? That M1 equals 3M2. So we know that ratio. And since we're doing these sequential, that condition still holds. That doesn't change in the 3-ball problem because that collision needs to happen in a way that holds M1 constant, or at 0, V1F equals 0, and then all we got to do is deal with the second collision. But obviously we don't want this one to fly up anyway, so we'll keep that one equal to 0. And we'll keep this condition. Really the name of the game is to get this condition. What's the mass ratio of these 2? It's not just going to be 3 again. Okay. It's not just going to be 3 because it's a different situation. Here we had M1 and M2 going at the same speed when they hit each other, just opposite directions. Here they're not going at the same speed. Right? This one is still coming down at VI, but this one is now going up faster. So we've got to calculate how fast was M2F rebounding. How fast is it going? So how fast is V2F in this collision, in the 1 to 2 collision? Well, if you recall in the lecture, that's actually how we started. We wrote down the expression for V2F. We realized we didn't need it. We needed V1F. But let's go back and remember V2F, it was the 2M1 over M1 plus M2, V1I, plus the difference, M2 minus M1 over M1 plus M2, V2I. That was the general elastic collision. So what we got to do is take that and say, okay, how fast would it be if we have the ratio of 3 to 1? So let's see, we can do this. I know we can do this. It's even the right numbers. V2F equals, it was 2M1 over the sum, right? So that's 3 times 2 is 6M1, or we'll just call M, 6M, over the sum M1 plus M2. Well, that's 3 plus 1 is 4. So over 4m. Right, because that's m2 really, right? Write it that way. So that's the 2m1 over m1 plus m2. And that was times v1i. v1i. Right? Which in this case was just v initial, right, going up. I think I'm doing for the positive direction is up. Right, so v1i, it was going v initial, and it was going up. We don't need the I, the 1, we just need the I, and this is positive. Okay. The second term is the difference, m2 minus m1. Oh, I'll just do it. m2 minus m1, that is m minus 3m. So it's minus 2m, m2, over, and then again the sum, over 4m. Right, and that's times v2i. In this collision, v2i was vi down, right? So it's negative. So times negative vi. See that? So what is this? It is, let's see, the m2's go away, right? Those cancel. This is 3/2 vi, and this is minus 1/2, but it's minus minus, so it's plus. So it's 3/2 vi plus 1/2 vi, it's 4/2 vi, it's 2 vi. So v2f, 2 vi. So in the end, this thing bounces up twice as fast. Very nice. So now we've got to do the second collision. So that was one collision. Now we've got to do the 2-3 collision. And it's the case that this one is moving down at vi, this one is moving up at 2 vi. We want them to hit, have an elastic collision, and figure out what mass ratio do we need to have this one stop. Right, so there's a new v2f. Right, so I forgot what notation I plan on using here. Yeah, so let's write those down. So v2i equals 2 vi. Right? So this one is going to move up at 2 times the original, and then v3i equals minus vi. It's still falling. Okay, so now we're set. And what we want is v2f to be 0. And we'll figure out what condition does that require to happen. All right, so let's look then back again at, now we're going to look at, this is sort of like used to be mass 1. We want to look at what's the condition for the one going forward to have 0 velocity. What is going to be required here? So we could figure that out. Let me look back at my old notes and say, okay, so this is sort of the old v1f formula, but we're going to write it as 2 because 2 became 1 and 3 became 2. So v2f equals, okay, so it is a difference over sum times v2i, right? So it is m1 minus m2 over m1 plus m2, but now it's m2 minus m3 over m2 plus m3, and that's times v1i in the old system, but now this is v2i, right? And v2i is 2 vi. Okay, that's the first term. And there's a second term. That's the 2m term. It's usually 2m2 over the sum, but now it's 2m3 over the sum because we're doing this for different ones. 2m3 over m2 plus m3. And that's times the second one's initial velocity, which is minus vi. Right? So that was one of those two general elastic collision equations, and we want it to be equal to 0. Okay, this is what gave us 3 before, but now it's not going to give us 3 because we're going in at a different speed. Here we go. It's equal to 0, so I can cancel the VI's. Right, it's equal to 0, so I can cancel the common m2 plus m3. And what I get is it's 2m2 minus 2m3 minus 2m3 has to be equal to 0. 2's all go away, and you get m2 equals 2 times m3. So mass 2 has to be twice the mass of m3. So basically what that tells us is if this is a mass of 1, this has to be 2, and this has to be 6. you want 6, 2, 1. And if you have that, when you drop them, this one will stop, and this one will stop, and this one will go. And since this one gets all the kinetic energy, it'll go the highest. Okay, this is what the ping pong ball did a minute ago, except the tennis ball didn't really stop. So to make that happen, I have here in my plethora of bouncy balls I now own, I have 3 that were pretty close. This is 89 grams. So this is basically 90, we need the next one to be 30. This was like 37, so I scraped a bunch of it off with a razor blade and got it down to 30. And this is another factor of 2 down, this is 15 grams. So if I can get these to fall right, what we should see is the top one will fly up in the air and the bottom 2 will just sit. And I'm not going to be too ambitious with how high I drop them from. Let's see. And there you can see, little ball flew and these 2 kind of just hit and rolled away.